I would like to get started on this next renewable energy source. It's called hydroelectricity. And we are on page 354 in your book. And you can see a lot of interesting statistics here to start out. You might recall from the pie chart that we studied in chapter 12, about 7% of the electricity generated in the United States is hydroelectric. And more than half of that is only in 3 states, Washington, California, and Oregon. Well, it shouldn't surprise you that that is so given the mountainous terrain that they have in these states. And because those states are mountainous and there's plenty of snows and therefore plenty of water flowing and snows melting in the spring, it's a very good opportunity to take the power of water falling to use it to spin a turbine that spins a ball of wire inside a magnet and makes electricity. China is the world's leading producer of hydroelectricity. Brazil is second, and then we come in third. Hydroelectricity basically works by the power of falling water. There are 2 different types of hydroelectric power. One is called a run-of-the-river system, and you should remember this one because it's environmentally better, friendlier than water impoundment system. When you see that word impoundment, that means that you are capturing water. So a water impoundment system is the classic example of a big dam with a reservoir behind it holding water back so that it can control the flow and make that turbine spin. These run-of-the-river systems are generally much smaller scale, and instead of building a big dam, we just take the power of the water as it falls. We don't control it nearly as much, but you can imagine it's much better for the environment. The big dam isn't in the way from fish and wildlife. There's not a buildup of sediment behind the dam. That's what siltation is. Siltation is the buildup of sediment as the river flows and then hits that dam. It drastically slows down the flow of the river. When river water flows, there is dirt suspended in it, sediment, and that sediment gets trapped behind the dam. Siltation then is a real threat to a well-operating hydroelectric system. I will also cover tidal systems because that's an interesting new way to use water to make electricity. This diagram shows you how a typical water impoundment system works. First, you have to build a big dam, and that big dam holds back the water. As the water gets held back, it needs to go somewhere. When you open up a small little opening, this is called a penstock, and allow that water to go, it comes rushing down the penstock, and that spins the turbine, that spins a ball of wire inside a magnet, that's the generator, and it makes electrons flow on a line and go to people's houses. That water's got to go somewhere, so it ends up in the river. But the water that's held back is much greater than the water that comes out at the bottom. This diagram doesn't really show it, but in most cases, when you see a dam and a hydroelectric plant, the river downstream, down here, is but a trickle of what it used to be. And if you have a river where there's lots of waterfalls and therefore lots of dams, that water that's left behind after it goes past dam after dam after dam gets smaller and smaller and smaller. And that's exactly why the Colorado River, for example, is but a trickle when it reaches the Pacific Ocean in Mexico. So let's summarize the advantages and disadvantages of hydroelectric power. It is clean. No CO2 emissions with hydroelectric power. Now, in the book, it does mention that you have to attribute some CO2 emissions to the construction of the dam, but during operation, no CO2 emissions. It probably took a lot of CO2 emissions, though, to build all of this concrete and to actually build the dam. That has to be considered when you do the math. The electricity is extremely low cost, extremely high efficiency. And the power of the falling water can be quite high. It all depends on the height of the dam, and it depends on how fast the water is flowing. Both of those things influence how much energy you get out of the dam. In fact, they had some statistics in the book here talking about, for instance, in China, the Three Gorges Dam produces an incredible amount of electricity, about 18,000 megawatts, whereas our largest dam, the Grand Coulee Dam in Washington State, produces about 6,800 megawatts. So it's China's is about 2.5 times more powerful than our best hydroelectric plant. One of the good things about a hydroelectric plant is you're controlling the river's flow. So you can provide control of flooding downstream. If there was no dam here and there was an excessive snowmelt, then this river would be flowing and the river might jump its banks further downstream. This way we can hold back the water with the dam. Provides water for year-round irrigation. This is a reservoir. I mean, that's what the thing is called, right? It is holding water. So that water is easily accessible for farmers, whatever. And don't forget another important thing. This river might have been pretty skinny as it flowed all the way down. Now you've got a big, wide reservoir. You've got a lot of waterfront property for people to buy. People love to live on a lake, more so than a river, because you can enjoy boating, fishing, all those kinds of things on the reservoir. The big negatives, it's very costly to build to start with. All right, it costs a lot of money to build that dam. Now, once you build that dam, the cost of the electricity is pretty low. So there's a very high upfront cost. There's a lot of environmental impact. Think of the habitat destruction that happened when you built this dam. This was probably a skinny river once that flowed nicely and naturally. And now you have put a lot of what used to be land underwater. In fact, scientists believe, more than one study has indicated, that even though we say there's no carbon dioxide emissions, the fact is all of that, all those trees and grass that you covered with water is now going to start to decay, and during that biomass decay, it happens anaerobically and methane is released, especially in tropical regions. That methane, of course, is a far stronger greenhouse gas than CO2 is. It floods natural areas. It converts land to lakes. Not a surprise there. You always have to worry about a collapse. What if this thing crashed? There's people living, along the riverbank that's rather skinny now thanks to the dam. You can imagine what happens if that dam breaks. It uproots people and decreases the fish harvest. We've talked about this before, and that's why we have these things called fish ladders, so that the fish can get upstream. I'm sorry. This bullet is really not talking about the life cycle of the fish as much as it is just talking about not having very many fish down here. So people that love to fish below the dam aren't getting nearly as many fish as people here in the reservoir. And you have that problem called siltation. Lots of negatives with hydroelectric power, But if we're worried about the greenhouse gas emissions, you gotta love hydroelectric. This picture's in your book. I think this is the Glen Canyon Dam. You can see it's a tourist attraction. Lots of people come to visit just so they have a nice view of things. And we have this very, very large reservoir. Millions of people visit the reservoir every year. And of course, it offers great recreational opportunities. This was an example of a dam removal, and it's true that in the United States we have actually taken to blowing up dams, getting rid of the hydroelectric power because of its damage that it's doing downstream, and just trying to improve the ecosystem by getting rid of or dismantling hydroelectric dams. It may be true that eventually most of our hydroelectric dams will have to be dismantled or at least dredged out because of that siltation problem. As you saw from the animation, if that siltation builds up behind the dam up to the penstock, then that's going to slow down the water flow that's going to the turbine to make the electricity. All right, a word about tidal power. Now, what we're trying to do with the tides, and you need to think about this for a minute, the awesome amount of power that could be provided by the changing of the tides. But this only works in areas where the high tide and the low tide have a very, very large difference. I used these pictures for you. This is called the Bay of Fundy, and this area of Nova Scotia, Canada, actually has one of the biggest tidal changes that there are. This is mid-tide, this is low tide. Every day. So you can see how much water is moving twice a day, every day. If we could find a way to harness that power of all of the water of the world, having its tide change twice a day, every day, that would be an awesome amount of power. The problem, of course, is how do you harness that power? You've probably been in the ocean when the tide's coming in. There's not enough power in that water to knock you over. You don't get great power out of the force of the tide coming in or going out. So remind me to tell you how the few countries that use tidal power do it. It's an eyesore out in the ocean, and it's got its problems. You got to run wires somewhere to hold the water back, but it is being done in countries like France, Korea, and Canada, places that have a big difference in tides. I experienced a big difference in tide when I was in the Navy and I visited Singapore. They have a very large difference in their tides every day. So let me explain more about tides later. And I think this is our last bullet of the day. These videos I would love to show you during class. So that's what I'm going to do. Remind me to show you these short little snippets, these short little videos. So we have large-scale hydroelectric power. That's the big dam scenario. Small-scale hydropower, like this picture that we saw here a minute ago. This would be a small-scale hydroelectric project, small-scale dam. Not a whole lot of electricity coming from it, but it all contributes to the grid. OTEC is something that we can talk about. There's not much to tell you. Except that I have seen it on the AP exam before. That stands for Ocean Thermal Exchange. And basically what you're trying to do is take advantage of the temperature, thermal exchange, take advantage of the temperature difference of the oceans to make some electricity. I'll explain that in class. Tidal power, I think we've already talked about. And again, I have a video to show you about tidal power, and I have a video to show you about wave power. Yes, why not? You've all been hit with a wave and it's knocked you over, correct? Waves are powerful. Let's find a way to harness that wave power, get it under control, and get it to spin a turbine that turns a ball of wire inside a magnet. I think that's it for hydroelectric. Yes, it is. The next thing we'll cover is solar energy, both in terms of using the sun's rays directly and also using the sun's rays to make electricity through something called photovoltaic cells. All right, nice, short, and sweet. Wouldn't you agree? After solar, we have geothermal, then we have wind, and then we have hydrogen. So we still have a long way to go to get through this chapter. See you later.